Hello everybody! So today we are going to write some Michelson. So Michelson is that mystical language that lives on the Tezos blockchain that we use to write smart contracts. So today I want to make a quick introduction about Michelson, and at the same time also introducing the FA1.2 standard on Tezos. So, we are going to write a smart contract that implements that standard. So a very simple smart contract, and we are going to write it directly in Michelson. So there are a lot of ideas going around about Michelson, that it's a complicated language and you shouldn't touch it. And actually, you're going to see today that it's actually pretty easy to write yourself, as long as the contract is not very complex. You can write contracts directly in Michelson. It's actually pretty fun, or at least I'm going to try to make it look like that. So we are going to talk about different things in this tutorial. So of course Michelson, but also the FA1.2 standard on Tezos. And I also want to show you how I write Michelson when I do. So of course this is, I'm going to introduce some personal preferences. So you don't have to do it like that. That's the way I prefer doing it. But in general, that's the way that works for me. So you are free to use it, or to find also your own way to write Michelson. So just a quick introduction, a quick presentation of how I write Michelson. So you can see here on the left side, we are going to use the Michelson ID from SmartPy. So in my opinion, that's one of the best ID in the Tezos ecosystem at the moment to write Michelson by hand. Here on the left side, you will be able to write the code in Michelson. And on the right side, the ID is going to tell you if you have errors. It's going to compile the code and check that everything is correct. On the right side, we are going to keep two websites open. The first one is the Michelson reference. So this one is not really the official Michelson reference that you can find on GitLab. This is the Michelson reference that's provided. I mean, okay, it's still on GitLab, but it's not like the dry one, the official one. This one is more. It's a reference that's provided by Nomadic Labs that I find more intuitive and also a little bit easier to use. So you can see, like, you're going to have all the details that you need about Michelson, and that's something that I keep open all the time when I write Michelson, because I don't write Michelson very often, so I forget things. I forget how some instructions work, or what they do, or how to use some of them. So that's something that's totally normal, and so I keep the Michelson reference open, and I check it when I don't remember how to use certain instructions. And at the same time, while I'm going to write the contract, I'm going to write it completely live. So I am going to make some mistakes. There are some things that I'm not going to remember. I haven't written Michelson in a few weeks already. So, but I think it's a very good learning opportunity. You're going to see how I struggle writing Michelson, and how I solve, how I'm used to solve issues when I write Michelson. So I think it's very good to show these problems that you encounter when you write Michelson, and how to solve them quickly. The second website that I will keep open is the description of the standard, of the FA1.2 standard. So a quick explanation of the standard. The FA1.2 standard is a standard that we use on Tezos for fungible tokens. It was one of the first standards that were written and introduced on the Tezos blockchain. So there are a few tokens that implement this standard, and that are very famous on Tezos. For example, KUSD is an FA1.2 token. CTES is also an FA1.2 token, so it's still a relevant standard to know, and you will see that it's a very simple standard. So the interface is pretty simple to implement in Michelson, so that's why I chose it for this tutorial. And at the same time, the behavior of the contract. So you can see that there are two entry points. One called transfer that we are going to use to transfer token from one user to the other, and there's another one called approve, where you will be able to approve a certain amount of tokens that can be spent on behalf of a user. There are also a couple of views, 3 of them, that we are also going to implement in Michelson. And we will have to read a little bit the standard and go through to check the different behaviors of the entry points. And as you can see, like the behaviors are very simple, so they're going to be easy to implement in Michelson. So that's it. So on the left side, we're going to have the IDE, and on the right side, we're going to keep the Michelson reference and the explanation of the standard open, so we can reference them and have a look while we write the code. So without further ado, let's write some Michelson. So Michelson first is the language that we use on Tezos to write smart contracts. So it's a stack-based language. So what it means is that we are going to use instructions to manipulate a stack. So a stack is just some values that are stored one on top of the other, and we're going to manipulate their position in order to change the behavior of the contract. So it's not the kind of language that you're probably used to write if you write something like JavaScript or Python, where you use some high-level concepts like variables. So that's not something that, for example, variables don't exist in Michelson. We don't have variables, but you're going to see that at the beginning it may look a little bit strange to write, but actually it's like a puzzle, you know, like you have to manipulate a stack of values, and then you can change these values. You can like use 2 values together to add them or to put them in a pair. There are different manipulations of that stack that you can do in order to update the state, and at the end update the state of the contract. So it's storage. A Michelson contract has 3 parts. And the first one is going to be the type for the parameter. So every time you interact with the Michelson contract on Tezos, you have to send a value of the required type. So technically speaking, there's only one parameter that you can send to a contract, but we're going to see how to implement an interface for the parameter where you can actually target the different entry points of the contract. The second part of the contract is going to be its storage. So the storage is the state of the contract. So that's why you're going to record all the values necessary to operate the contract. So here, for example, in an FA1.2 contract, you want to have, for example, a ledger where you're going to record all the balances of the users and also all the approvals, the balance, the values that were approved to be spent. So we're also going to see that. And the third part of the contract is, of course, its code. So that's all the instructions that you have to use in order to manipulate the parameter that is going to be sent to the contract, and also the storage of the contract. So that's what we're going to do right now. So right now we're going to start with the parameter. So you will see that the IDE is a little bit sensitive. So I'm going to take some. I have some personal techniques that I use in order to silence the the compiler on the right, so I can write my code. So I'm just you're going to see that I write dummy code on the left side just to silence the compiler, but later we're going to update it. So for example, just to show you like the structure of a very simple Michelson contract, here we're going to have the parameter with the type that is expected. So here we're going to put int, but it's a dummy value. The storage, let's put also an int. So here we have parameter and storage, and then the last part is the code. So you just write code, then you open curly braces like that, and now you can start writing your code. So at the beginning of the execution of the contract, you're going to have a pair on top of the stack. So all the time, and you're going to see it also in the IDE. Every time that you write Michelson, you have to imagine that stack, that where all the values are pushed on top of each other, and how you can manipulate it. But you will see that the IDE makes it very easy for you to follow what's happening on the stack. So here at this point, there is a pair that's pushed on the stack. On the left side of the pair, you're going to have the parameter that was sent to the contract, and on the right side of the pair, you're going to have the current storage. So right now we're writing dummy code. So I'm just going to use an instruction that's called drop, and this instruction is just going to remove the element that's at the top of the stack. And then here I can use push int, let's just say 5. Okay, so now I'm pushing. So push is an instruction that's going to put a new element on top of the stack, and here it's 5 of type int. And at the end of the execution of a Michelson contract, you have to return a pair with on the left. In the left field of the pair, you must have a list of operation, and on the right side, you must have the storage, or the new storage if you updated it. So that's what we're going to do here. So push int 5, that's going to be our new storage, our dummy storage, just to see how it looks like. And now we're going to. So nil is an instruction that pushes an empty list on the stack, and so there are 3 types of instructions in Michelson, and we have the 3 types here. So the first type is like a bare instruction where you only have the instruction itself. So like drop, and there are also other instructions that we're going to see throughout this tutorial. The second type is an instruction that takes one parameter, for example nil. So nil pushes a list on top of the stack, and you have to provide the type of the elements inside the list, even if the list is empty at the moment, but you still have to provide the type of the elements. And here the type is operation. And then you have the third type of instruction is an instruction with 2 parameters, like push, where here in this case you will have you have to provide the type of the element that you're pushing on the stack, and then you have to provide the value of that element on the stack. Okay, so now so here the way the IDE works is that it's going to show you this here on the. So here you have let's put it row. And then so here you have the instruction, and then here you have the state of the stack. So here the stack is empty. Now we have an int. Now we have a list of operation and an int. So now you see that we have those 2 elements that are supposed to be inside a pair to be returned at the end of the execution of the contract. So now we have an instruction called pair that's going to pair the two elements on top of the stack together and push a new pair on the stack. And now you see that the compiler is happy because we finished the execution of the contract with the pair containing a list of operations on the left that's empty, and the new storage, which is an int. So that's a very, very minimal Michelson contract, and you see that's pretty easy to understand. Now we're going to start writing the parameter for the FA1.2 contract. So we're going to have a look at it. So the parameter is the value that's going to be sent to the contract when you want to update its storage. You can see that we have two, according to the standard, we have two entry points, transfer and approve. And those entry points are going to accept different values in order to update the storage. There are also some views that we're going to implement a little bit later. At the moment, we're going to focus on the entry points, so transfer and approve. So the way you do that, if you remember a little bit earlier, I said that technically speaking, you only send one parameter to the contract, but here you see that we expect two of them. So the way you do that in Michelson is that you're going to use a type that's called a union type, and then inside the code we're going to be able to know which, so a union type is a type where you have two different values on the left and on the right, and then in the code of the contract you're going to be able to tell if the parameter that was sent targeted the left side of the union or the right side. So the way you do that is like that. So OR is the type for a union, and now you need two types, like for example int. So that would be like a very simple one. Here we can see that we have two entry points, so we will have to handle that, and those two entry points have two annotations. So an annotation is like the name of the entry point, and you have to provide them. So at the Michelson level, they're not that important. So I mean, the Michelson doesn't during the execution of the contract, Michelson is not really going to care about the annotations, but they are very important if you start writing a DApp. Because tool like Takedo, for example, to interact with the smart contract on chain from JavaScript is going to depend a lot on these annotations. So that's why it's better to provide them, and it's going to make your life easier later if you write the DApp for your contract. So let's do it here. So we're going to have two fields here, and I'm going to put parents because I'm going to have to write their annotations. So let's start with transfer. Here in transfer we see that we have a pair where on the left side we have an address for the spender of the tokens, and then on the right side we have another pair where on the left side of this one there's going to be the address of the recipient, and then there's going to be the value, the amount of tokens that have to be transferred. So the way we're going to do this is, so we say that there's a pair here, and then the annotation for the pair is transfer. Oops, let's write it properly. Transfer. And then you can see that there are also annotations for each field of the pair. So we're going to have to be careful with that too. So because it's a pair, we also have two elements here. The first one is of type address, so that's the spender, and it's called from. And the second type here is another pair, this one here, oops, this pair here. So this one is another pair where we also have two fields. The first field is an address with the annotation 2, and the second field is a nat. So nat is a natural number, so it means 0 and above. So a natural number can never be negative because, well, you cannot transfer like negative values of tokens. So it makes sense in this case. And here we have our first entry point. We're going to just make it a little bit nicer like that so we can follow what's happening. So OR, okay, so that's the first branch of the OR. And now we're going to deal with the second one, the approve entry point. This one is going to be a lot easier to write. It's a single pair, so it's not, there's no nested pairs. And so we have an address on the left and a NAT on the right that are also annotated. So you have to be careful with that. Oops. Doesn't let me write the code first, but that's okay. So address, spender, and this one is is a NAT that's called value. Okay, so you see the parameter is very simple. So because it's a very simple tutorial to introduce Michelson and the FA1.2 standard, I am not going to write other entry points, like for example to mint tokens or to burn them or whatever you would like to implement in your contract. But just know that if you would like to do that, the way to do it is to have nested unions. So here, instead of having a pair, you would have another OR with two branches for the OR. So that's how it works, and that's how you emulate like different entry points for your contract. So here the compiler is happy, so it looks like it's fine. Now we're going to have a look at the storage. So for the storage, you probably understood from the entry points that we're going to need some kind of structure to record the balances for the users, and also another structure to record the allowances that were approved by the users. And actually, if you scroll down here, you're going to see that there is a storage type that's recommended. So it's a big map. Actually, we can just like copy it and paste it here. And okay, so you see that kind of error. So it's probably because I have to put it between. Okay, so here we're going to use a big map. So a big map is just like a hash table in Michelson. So you're going to use keys. It's a table of key and value pairs. So you have a key that points to a value. So all the keys are unique, of course, and they point to different values. Here the big map is going to be called ledger. On the left side, so the key is going to be an address. So it's going to be the address of the owner of the tokens. And here you have the value that's going to be stored in the big map, and this value is going to be a pair. So here on the left side, you have a NAT value that's going to be the balance of the user, and on the right side of the pair, you have a map. So a map is like a big map, but all the keys and the values are visible. So in the big map, they are serialized and you don't have access to them. So you need to know the key in order to access the value. In a map, it works differently. It's not serialized in the same way, and so you have access. You can see all the keys and the values are publicly available. And so here on the left, as a key on the map, you have an address. So that's the address of the spender that's allowed to spend the tokens on behalf of this user, and then that is the amount of tokens that they allowed the spender to spend on their behalf. Here of course we have a problem in complete stack. It's because I push this dummy value here, and of course it doesn't work anymore because the storage is expected to be a big map, and here I push an int. So we're going to have to write some different dummy code, at least to make it compile, just to be good here. So instead of dropping it, what we're going to do is that use an instruction that's called CDR. So CDR is going to, so you remember that at the beginning of the execution of the contract, we're going to have a pair on top of the stack, where in the left field we have the parameter, and on the right field, in the right field we have the storage. So CDR is an instruction that's going to extract the right side of the pair and push it on the stack. So it's going to consume the pair. So in general, a lot of the instructions in Michelson work like that. When they use a value that's on the stack, they also consume it. So that value is gone. So that's why you're going to see when we start writing the Michelson code that we are going to duplicate a lot of the values that are on the stack because we need to use them later. And here, so here when you use CDR, it's going to consume the pair that's on the stack, and it's going to push the value that's on the right side of the stack, of the pair, sorry. So here we push the storage. The counterpart of CDR is CAR, where you get the left side of the pair, and here you see it clearly. You see here we have the parameter, and of course it doesn't compile anymore. While when I write CDR, now I have the storage on the stack, and of course here I have I created an empty list of operations, and I have the storage. So you have to imagine that here it's a stack where the first element is that list of operations, and the second element is the storage. And here I pair them together, and of course the compiler is happy because I return the expected value at the end of the contract. So here now we have our parameter and we have our storage, and we can start writing the actual code to manipulate the parameter and the storage, and update balances, update allowances, and do some cool stuff with our contract.